Afternoon all, it's Postbag, and this one came via TNT. So let's see what we've got. So this is Microchip development tools, and inside here we have this. It's a little Microchip microcontroller development board. It's the PIC10F322. So inside all that packaging, essentially we have this. It's a Microchip PIC microcontroller development board. Now the PIC itself is this tiny little 6-pin SOT23 device here, U1. And also on this board are two LEDs wired to two of the I/O pins, a pot, which presumably is connected to one of the ADC inputs, and a little push button switch. And then there's also a little prototyping area here with a row of ground pins, a row of VDD pins, and then just a bunch of pins which are available for whatever use you want. And also in there is a PIC10 brackets LF, so it's either the 10F32X or the 10LF32X. I think the device on the board here is a 10F322. And inside we have some diagrams showing what's what, and also a circuit diagram, so you can see how the microcontroller up here is connected through links to the peripherals, well, peripherals, two LEDs, a switch, and a pot. Now it looks like from the layout of the board and also from the circuit diagram that the ICSP header, this is the serial programming header, is directly connected to the chip. Those lines then run down here to this top connector J2, so that's J2 there on the diagram. They're pre-linked, so actually you've got PCB traces linking J2 and J3, and it says you actually have to cut them if you want to isolate these, and then you'd put in little header pins and links to link them back up. And then J3, which is this bottom row, runs off to all the peripherals, the LEDs here, the switch, and the pot. So it's all pre-wired up. Now this 6-pin ICSP is compatible with the PIC programmers. Now I have, because I'm a bit of a fan of Microchip PIC microcontrollers, both the PIC2 and the PIC3. They don't appear to be in their boxes, so I'm going to have to try and find those. So I found the PIC3. It's in here amongst my ZIF sockets, because I was using this to program my microcontrollers for the solar charge controller. So that's the PIC3 located. So the way this works is that this plugs into that header, like so, and then the PIC3 has a USB. This is a USB mini, so that plugs into the PC, and then you use Microchip's MP Lab integrated development environment to start programming this chip. But let's have a closer look at this actual microcontroller. So this is a very tiny device. It's a SOT23-6 6-pin. You can see how big it is from these 0.1 inch spaced pins. Let's just put a magnifying glass in front of it. And there's the device. It says, what's that, LJ10 on it. But despite this thing's very small size, this is quite a powerful microcontroller. If you have a look at the datasheet here, we've got up to 16 megs clock, and that's going to be a built-in clock, no external clock circuitry required. 512 words of flash program memory, 64 bytes of data memory, an 8-level deep hardware stack, interrupts, processor self-write so that you can write to the program memory as though it's kind of E2 PROM. It allows you to save non-volatile data. This is a 6 or 8-pin microcontroller. Obviously the SOT23, this one here, is 6-pin, but you can get it in a 8-pin dual inline chip, although two of the pins are not connected. So here's the 6-pin SOT23. We've got a VSS and a VDD. and then the other 4 pins are I/O. Now one of them is a bit special because it's also the master clear and the programming pin. So RA3 can be digital input only, but the other 3 can be analog inputs for A to D, digital inputs, digital outputs, and there are a whole host of peripherals on this chip. Let's just look at the 8-pin one for a moment. You can see that pin 1 there is not connected and pin 6 is not connected. So essentially that's also a 6-pin device. So let's have a look at some of the microcontroller features. We have low power 16 meg internal oscillator. It can also be wound down to 31 kilohertz if you want to run the thing really slow. Wide voltage range. The LF can go from 1.8 to 3.6 volts. The F, which I think this is, can go from 2.3 to 5.5. Power on reset, power on timer, brownout, sleep, watchdog timer, code protection, selectable oscillator options, external or internal, in-circuit serial programming, and so on and so forth. Let's have a look at the peripheral features. We've got 4 I/O pins. 1 is an input only. The rest are input or output. High current for LED driving, also interrupts, weak pull-ups. We've got timer 0, timer 2. We've got PWM, 10-bit PWM, analog to digital with 8-bit resolution on 3 channels. Now, configurable logic cell. That's a fascinating device. I'll have a look at that in a moment. You can set it up to be an AND, an OR, an XOR, or a D flip-flop, or a D latch, or an SR, or a JK flip-flop. What else? We've got a numerically controlled oscillator. That looks like an interesting device. We'll have to have a play with that. Complementary waveform generator, also built into this thing. That should be fun too. So I think one of the most interesting peripherals on this chip is the configurable logic cell. Here it is on page 104 of the 187-page datasheet. And because of the complexity of coding the configurable logic cell, it actually comes with its own application, which you run separately to generate code for this peripheral. So in this little application, we pick the device here. This is the PIC10F322. Which of the gates we have? There's only 1 in this device. In some of the other microcontrollers there are more. We pick the type of logic cell we want, so we can have AND OR. There's a general gate array at the beginning. Then you can have AND OR XOR, just a simple AND gate, a set reset latch, a D-type flip-flop, an OR gate with a D-type flip-flop, a JK flip-flop, or a D-type latch. And then on the input, you decide what you want to trigger each gate. So let's take this one, for example. We can have either input RA0 or RA2 as an input. We can use the output from the PWM oscillators as an input to the configurable logic cell. We can use the numerically controlled oscillator, or we can use the main high frequency clock or the low frequency clock. So let's just take one of the input pins, and then you can decide whether you link that through to this gate, or whether you link it through inverted, or whether you cut it. So you might link this gate on the second input, this gate on the third input, and this one on the fourth, for example, but we want that one inverted. Completely flexible configurations. Now you could do something really silly, like link 2 of the inputs into 2 gates and then into this AND gate, and the output to a 3rd pin on the device. The machine could boot up, set up its configurable logic cell as just an AND gate, and then go to sleep. So you'd have a microcontroller that turns itself under program control into an AND gate. And from that point on, it's just a simple AND gate. Bit mad, but it could do it. Now, what about the numerically controlled oscillator? It uses, it's a timer that uses the overflow from the addition of an increment value to divide the input frequency. Yes, is most useful for applications that requires frequency accuracy and fine resolution at a fixed duty cycle. So this is a controllable high precision oscillator. So here's the block diagram of the numerically controlled oscillator. All looks very complicated. It's all inside this tiny little chip. I think I might use this for some sort of stylophone, you know, one of those sort of simple musical instruments. Now, what about the complementary waveform generator? Here's the block diagram. This can generate complementary outputs from any input so that you can have, it's mainly going to be used for driving MOSFETs for high side and low side. You can create dead bands, non-overlapping waveforms for things like motor control and that sort of thing. And it's hard to believe that all this complexity is inside this tiny chip, which I'm having to use 2 magnifying glasses to even get a picture of it. It's absolutely minute. And this development board is this part number here. It was £8.55 direct from Microchip on the Microchip Direct website. Now this price, of course, is excluding VAT, and there's also nearly £5 of postage for this thing. So it ended up costing nearly £15 to buy this. So I've been doing a lot of Arduino programming recently, and also started looking at programming the ESP8266. I thought it'd be quite fun to get back into PIC microcontrollers and program one of these tiny chips.